Well, it's a great pleasure to be here. Actually, was an undergraduate here a long, long time ago, so I kind of know my way around. But it's wonderful to be back, and I'm digging in slowly. But I'm going to talk about a number of things today in kind of this myths format to give you a little bit of introduction to some of the things that I've been interested in working on, and also things that I think are fairly important. Actually, the first one is really not my own work, but it's something I've been pretty interested in, and I'll talk more about that. I do work at Penn State University, and I wanted to start out by letting you know, because not everybody out here realizes this, that Penn State and Berkeley are the two leading institutions in the world in terms of research around energy and fuels. And you folks at the Energy Bioscience Institute probably had a good idea that Berkeley was a great place to do that, but you may not have known that that's true at Penn State. And you can see the other locations. The DOE does have, and this is by order of citations in the most recent 5 years that there's data. So the national labs do have a lot of activity, NREL in particular. I could talk to you a little bit about that. A lot of those publications are some tables that they put out on solar energy, which get 500 citations every 6 months, so a little bit different. The questions I want to talk about today are these 5. So one of them is about what's commonly called the blend wall. Do we already have so much ethanol from corn in this country that we really can't handle any more ethanol? Okay, so that's a very common thought. A lot of people believe it, and in fact, there are some very real components to that, and I'll come back to that in some detail. Another one that relates more to my personal research is the storage of biomass and when you should harvest it. We usually think that you should wait until it's fully mature and dry and then harvest it and then make something out of it. That may not always be the best strategy. Again, I'm going to come back to that. Sugar and syngas. Many of you are working with sugar as an intermediate. If you're looking at fermentation processes, syngas is also used for fermentation, but more commonly in thermochemical conversion processes. After that, people have a pretty short list. I think it might be time to revisit how short that list is and think about some alternatives. I'm working with carboxylic acids, which have some interesting characteristics. I'll just provide you with a little bit of a teaser about that. Is there enough cropland for both food and biofuel production? That's something that has created a lot of controversy over the last 6 or 7 years, and I've done a little bit of work on that, looking at it from a systems perspective that includes our diet here in the United States. Those of you who were here a couple of years ago when I was visiting and gave a talk, you heard a longer version of that. I'm going to just give you the 5-minute version today. And then the last one, which is something I'm going to be working on while I'm here, natural ecosystems. Do they sequester more carbon than managed ecosystems? We got some feedback on a paper recently that said, you know, this whole biofuel thing is a crazy thing to do on abandoned land. If we've got land that's abandoned, we should let it go back into natural ecosystems, because that's going to do way better in terms of carbon benefits from the planet than doing fuels. And actually, if you look at the last 2 questions and you take the common popular understanding that food and fuel are a conflict on cropland, and we don't have enough cropland, so we shouldn't use cropland, and you take the last question and say, well, natural ecosystems are better than managed ecosystems, so we should let them convert if they are abandoned, then we don't have any room left for biofuels at all, and those of you working on it could go home. But I think they are both myths that have some truth in them, but there's some other things to think about. So let's get into the first one, and I'm going to credit Jim Anderson, who's with Ford Motor Company, for a lot of the information here that he sent me. He's actually coming here this weekend for a few days, so I'll be meeting him Sunday morning. If anybody gets really excited about this and feels like they really want to talk to him, he might be available Monday or Tuesday. I'm not sure where in the Bay Area he's staying. But, the blend wall. So here is a very simple illustration of that. Essentially, most of you who have gasoline vehicles probably know that there's about 10% ethanol in those vehicles. That's been the case for almost a decade, sometimes a little bit more than that, but it was phased in as MTBE, another oxygenate, was phased out because of pollution problems. Ethanol has oxygen in it. You probably know that as chemists, and so that has good characteristics when you're combusting other fuels because that oxygen actually makes for a more complete combustion process. So 10% is the blend that we use very commonly today. All of our cars can tolerate it, although if you have a really antique vehicle, you might want to still use ethanol-free gasoline. And you can still buy it a few places. It's pretty hard to get. But beyond 10%, you either have to have a flex fuel vehicle or a new vehicle. And Ford and General Motors are warranting all their 2013-14 models for 15% ethanol. The EPA doesn't think that would cause a problem in any cars since 2007, but you can't really get it. And in fact, you can't very easily get flex fuel E85 in most parts of the country. So as a result, we're pretty much tied into 10%. And in this figure, you see that our typical fuel consumption of 130 or 140 billion gallons a year works out to, at 10%, 13 or 14 billion gallons a year of ethanol at that 10% number. And the demand for ethanol here has pretty much flatlined at that area. And in fact, we've had some challenges because projections 10 years ago were that this curve of total fuel consumption was going to keep increasing, but with the efficiency standards now that the auto manufacturers have pretty aggressively complied with, we're now seeing total fuel consumption drop, which means if you're stuck at 10%, the ethanol market shrinks also, and that's a real big problem if you're producing ethanol right now for corn, or if you'd like to make it from cellulose. And by the way, the mandates in the Renewable Fuel Standard are ramping up, and so the expectation back in 2007 when that law was passed was that there would be capacity to handle in 2014 and 2015, 14, 15, and I think 16 million gallons a year, or billion gallons a year of ethanol. And in fact, here is that law. This is actually from the Congressional Budget Office, a report they did earlier this summer, but the data's about a year old that they've been able to collect. So here's the increase in ethanol consumption. The biomass-based diesel, which is mostly biodiesel right now, but some of the alternative fuels that some of you work on might fit into that category if they're a diesel substitute. The standard was flatlined at 15 billion gallons a year of ethanol, and then a couple billion of bio-based diesel, but the biomass-based diesel can substitute for some of these other components. Cellulosic ethanol was expected this year to produce, I think, about 3 or 4 billion gallons. It might produce 20 or 30 million gallons, so we're only 3 orders of magnitude short. And one of the questions is, how do we grow this pyramid? And right now, as again many of you are aware, we're transitioning from thinking about cellulosic biofuels as ethanol, which is what we were thinking in 2007, to thinking about various kinds of drop-in fuels. They need a lot of research. That's supporting a lot of you to do really innovative stuff, but that's not turning into commercial products today. All right? So there have been some pretty big changes in expectations at the Energy Information Agency. It's part of the federal government that does these kinds of analyses and tries to project what we need. Back in 2007, this is what they expected the fuel system to need. This is what it's actually been doing, and this is what they're projecting forward, again, based on those efficiency standards the auto manufacturers are complying with. And here's what they were expecting in terms of cellulosic biofuels. Here we are, 4 billion or 2 billion gallons, I guess, this year, and maybe 3 next. And here's what they're suggesting is going to actually happen. So, oops. And by the way, that's only in 7 years. That's kind of radical change in thinking. So in that Congressional Budget Office report, which I'd encourage you who are interested to go ahead and read, they looked at a number of scenarios to try to comply with the Renewable Fuel Standard, which is the law of the land, and the EPA is trying to figure out each year how to best match it and how to blend some of these things together. And one of the scenarios that a couple of scenarios they looked at were based on an expectation that really the quickest way we can get a lot of fuel into the system is to use our E85 fleet that's already out there, but get some pumps on the landscape so people can actually fill up with that, okay? And then also to encourage and incentivize some other fuels. And they did some scenarios with E20 and E30. I'll talk a lot more about them. What they anticipated is that the price of, and actually this is of petroleum-based diesel, so with biodiesel blended in, of E10, so gasoline with ethanol blended in, and of E85, in order to really incentivize the E85 vehicle owners to buy E85 and get it into their tanks, and to incentivize the gas station owners to sell it, there would have to be a pretty big subsidy on E85 of almost $1 a gallon, roughly, and that would be paid for, so it would be costing less than $1 a gallon less for E85, and that would be paid for by 30 or 50 cents a gallon on the other two main fuels. All right. So gas prices are a really touchy subject in the United States. So this is not really the direction the EPA and Congress are likely to take, but that's where we are right now. What I'm going to talk about is some of these intermediate blends, E20 and E30, which have a lot more ethanol in them, and as I'll show you, can actually take care of the renewable fuel standards expectations pretty quickly. First, I want to give a little bit of a summary of what different kinds of ethanol are. Again, many of you will know that, but for those of you who don't, so these lower blends of ethanol, which would go up to E30 and also E85, are all anhydrous ethanol. So they've been dewatered to get the water out. And many of you understand that there's an azeotrope of water with ethanol. It's about 5% of water when it's in equilibrium. And so our gasoline vehicles don't usually like quite that much water, so we dehydrate the ethanol before we blend it with gasoline. And we try very hard to keep water out of the system. It is not impossible to burn ethanol with water. So in Brazil, they have hydrous ethanol, and there's some facilities now in the Netherlands with hydrous ethanol as well. It's a lot cheaper because you don't have to go through that, well, somewhat cheaper because you don't have to go through that dehydration process. So I mentioned that Jim Anderson works for Ford. Ford's a company that's been interested in ethanol for a long time. Their Model T was ethanol ready in 1908 when it first rolled off the assembly line. And Henry Ford himself thought that ethanol was going to be a tremendous fuel of the future. And he was thinking ethanol, and I'll show you why he was thinking of it, mostly because of its octane and the energy efficiency opportunities that creates. But he was also he'd probably be pretty comfortable with any drop-in fuel also. So this is just a really quick summary of some of the thermodynamics. So in a gasoline engine or a spark combustion engine, which is called an Otto engine, the efficiency can be calculated by a pretty simple equation. The thermal efficiency is 1 minus 1 over the compression ratio to a power that's the ratio of specific capacities of a volumetric and pressure-based constant, holding volume or temperature constant. So, what you see here is that as the compression ratio increases, and our vehicles today are mostly in the 9 to 12 compression ratio range, but most of Ford's trucks right now are in around 10. You can see that we're running about 45% thermal efficiency. By the time you get that combustion, that efficiency of thermal efficiency out to the wheels, you're down about 35% conversion efficiency of the fuel to get actually into moving down the road. And the curve here, if you can increase your compression ratio up to 12 or 15, you get some pretty good jumps in thermal efficiency. It's about 1% increase in thermal efficiency per 1 unit of increase in compression ratio. The Indy cars know this. They're running on E85, about 104 octane, and that allows them to run a higher compression ratio engine, which is more powerful and more efficient. This is Danica Patrick, so one of the IndyCar racers that some of you may be familiar with. All right, so here's some real data. All right, so this is Young et al. and Jim Anderson was a co-author on this, 2013. Ethanol gasoline blends in a turbocharged direct injection engine. So this is a test engine. They run it through various sequences, which are the same sequences that the EPA does to give the mileage numbers that are on the stickers of cars, which some of you know are not perfectly accurate, but it is the standard that we use for comparisons. Right? So what we've got here is carbon dioxide benefits, so that's reduced carbon dioxide emissions as a function of fuel concentration. So this is E10 with a research octane number of 91, E20 with a research octane number of 96, and E30 with a research octane number of 101. Over here on the right side, it's the miles per gallon benefits versus E10. So those are all normalized to 0 here. And over here, it was the CO2 benefits compared to E10. And here's the metro, EPA, and the highway cycles for running the engines. Right? So just so you see, there are some differences there. And the thing I want to note is that there are 2 compression ratio engines that they tested. One is a 10-to-1 compression ratio, and the other is a 11.9-to-1. So the green lines are always the 11.9-to-1 ratio. So when they did in their pre-testing, one of the things that they found, which didn't surprise them, was that the 11.9-to-1 compression ratio engine, you could run it on E10, but it really didn't run very well. 92 octane, it's knocking a lot, and that will wear out and destroy the engine over time. So that data is really not terribly relevant, but it's there for completion. That high compression engine did, however, so here's the baseline in each case, E10, and then here's the higher compression engine with the E20, and what you see is that has, under the metro driving cycle, almost a 5% increase in a reduction in carbon dioxide emissions per mile traveled, and similar on the highway. The miles per gallon benefits are slight, but increased in both cases over the base case. So many of you know that ethanol is expected to take a mileage hit. When you blend it in with your fuel, it's got less energy per volume. Thermodynamically, we know that. So you expect to get fewer miles. And when you run a conventional engine, especially a pre-2005 engine, that's what you'll get. The newer ones can adjust the timing based on the fuel characteristics and actually achieve a little bit better efficiency than those older ones. And then if you take advantage of the compression ratio benefits, you can get a lot better efficiency. Okay? So this is essentially doing a little bit better than break even at that 12-to-1 compression ratio. Now you'll notice for the E30, it does a little bit better in terms of the carbon benefit, or equal, than the E20, but it does take a mileage hit in miles per gallon. However, when they did that anti-knock testing, they also could see in that engine that the E30 could actually take an even higher compression ratio, probably 14-to-1. And so what I've done is roughly shown where that number might have been at a higher compression ratio engine. Those blue bars are not data, but they just suggest that, again, there's potential. Here is another sort of modest factor, but there are some synergies between ethanol and isoparaffins. So if you look at the actual theoretical research octane number based on the blend of ethanol with a baseline fuel that might be 82 octane or 88 octane or 92 or 95 octane, and you blend in your ethanol, you see the octane numbers go up, but these dashed lines are actually a little bit higher. Those are test values, and that's because of some kinds of synergies, which are not fully identified, but maybe with isoparaffins in the gasoline with ethanol. So they actually do a little bit better. All right, so now here's the interesting thing from a policy standpoint. So back in 2000, our E0, or standard unleaded gasoline with MTBE, was 92 octane. Okay, that was what we sold. That's what our cars were designed for. Here in 2010, we're 92 to 93 octane. But if we'd stayed with that same base fuel and added ethanol to it, we should be at about 95 or 96 octane. So what happened? Well, the petroleum refinery said, look, we have to put in this ethanol anyway. It's got extra octane. Let's use a cheaper grade of petroleum fuel and drop the octane number, because it costs money to provide, down to 88. All right, so that's the base fuel. So there's actually a potential social benefit here that's been captured by the fuel industry, who routinely is concerned about the cost of ethanol, but actually is managing to get a cheaper petroleum product into gasoline because of it. You don't hear that story very often. And you can see from this side here that if we stuck with any of those blends, but let's say the 88 blend that we're at now, and worked up to 20 or 30% ethanol, we'd get into a 94 or 96 octane ratio, and then all of those higher compression ratio engines would be possible. Right? So here's some analysis of what the renewable fuels, meeting the renewable fuel standard entirely ethanol, would do for the fuel system. And so here's, again, projecting forward to 2037, I think, is the year that this projection is to. Roughly just under 120 billions of gasoline or fuel demand, gasoline demand. Ethanol ramping up to about, I think it's 46 billion gallons a year. And at that blend ratio of gasoline to ethanol, we'd be just under a 30% blend, which is where some of these really sweet combustion opportunities happen in terms of engine efficiency. Okay? And this was really quite amazing to me. Ford is, and GM also, but Ford in particular, is perfectly willing to switch their vehicles to take advantage of this. They see some big opportunities. They've already committed voluntarily, you may recall this a few years ago, to increase the energy efficiency of their vehicles significantly by 2037. So they're going to more than double the efficiency. And they can do that with the existing fuel distribution, the existing octane number, but it's a whole lot easier for them to do it with a higher octane fuel because of that compression ratio opportunity to redesign engines. So what they proposed, and this is a 2009 article, is that by 2012, so we're already past that, they could make all of their vehicles either multi-blend vehicles that could go up to E20 or E30, or flex fuel vehicles. Right? So not exactly 10-year or 20-year away technology. And then if you look at the total fleet of vehicles in the U.S., if that were switched over at that point, then the conventional vehicles would still be around until 2025, the late 2020s. Eventually there would be just a few of them, antique cars like there are today, that still need non-ethanol gasoline. And the flex fuel vehicles would continue to ramp up, and those multi-fuel blend vehicles would really dominate the situation. And then here are a couple of projections for fuel demand based on this kind of a fleet and an introduction of new pump, not new pump technology, but pump availability for either, in the first case, just E85 and E10. So if we don't change our distribution system too dramatically, but at least get an E85 vehicle everywhere that there is an E85 pump everywhere there's an E85 vehicle, then we'd see this kind of ramp up, and the demand would be sufficient to keep up with the ethanol supply up until about the late 2020s, at which point, unless we started buying a whole lot more flex fuel trucks, which is most of what they are, we would suddenly have the same problem we're in now. But that's at least putting it off for another decade and a half. If there was the inclusion of the E20, so if we had additional pumps to actually supply that, then the expectation would be that we'd actually have way more capacity for ethanol into 2030 than we actually need. And that gives the work you're doing time to actually catch up and produce those drop-in fuels if that ends up being the appropriate strategy. I will mention, since I'm really interested in butanol, and some of you are, its research octane number is 92, so it's not going to have that same benefit. But one can imagine a blend of butanol and ethanol being pretty interesting in these scenarios. Okay, so that was myth number one. If you have questions, you can come back, and I'm going to go through the other ones, I think, a little bit quicker. I hope so. So the second one, though, I'll take a little bit of time with this too, because it's my own work, and I'm pretty excited about it. So biomass should be harvested at maturity and stored dry. So here's typical, I believe this is miscanthus being harvested. This is switchgrass being stored. Some of you know that this technology is pretty well established now. There are people that are using dry storage in cellulosic ethanol plants this year in Iowa and Kansas. And so we know how to do this. And we have some technologies that are looking like they're going to be close to cost effective on this basis. I'm going to talk about younger grasses and immature harvest. A lot of people think that's a crazy idea. Maybe it is, but I want you to think about some of the possibilities and potential benefits of it also. First of all, and I'm going to spend more time on winter energy crops, but most of what I'll talk about early could apply to immature summer annuals as well. So harvesting switchgrass in, say, mid-August, for example, when the biomass has already peaked on a dry basis, but before the plant is senesced. So the advantage of the winter crops is they complement summer annuals, and I'll talk more about that. They're also really easy to grow. Farmers are already growing many of them. Their existing equipment works just fine. And one of the advantages of an annual crop is you can use the existing farm finance system, which is actually struggling a little bit to deal with these perennial crops that might take 5 to 10 years to pay off the investment in originally planting them. And so a lot of people are concerned about that. All right, for many of you who are very familiar with plant physiology, some much more than me, but just to give you a sense as to the way these grasses mature. So these winter grasses put out a lot of root and then some biomass early. They then extend their stems, and as they start to flower, they go through this boot and heading stage and then eventually ripen. And you can see that there is a pretty rapid expansion here during this particular part of the cycle vertically. The biomass doesn't increase quite that fast because it's elongating. And in fact, the biomass typically gets close to a plateau right about here, okay, just before at flowering. And this period of flowering is actually pretty interesting because there's a lot of physiological process or metabolic change that goes on at that same time, which hasn't been, I think, nearly sufficiently investigated. One of the things that we know is that there's an increasing accumulation of lignin at that point in time, and that affects the biodegradable fraction, which is this green line here. And during that flowering period, that fraction tends to go down significantly. Now, this is new news to a lot of chemical engineers, but it's really old news to ruminant livestock farmers and animal scientists because they've been harvesting green grass for a long time to feed cows because they do a lot better on it. And what I'm going to share with you is some evidence that some of our refinery processes might do pretty well with that kind of material too. So just looking at this flowering period and noticing that real significant change in gradient of the biodegradable fraction is the focus of really this slide, which is some work that I've been doing with Li Lin's group at Dartmouth. Zhongjun Xiao is the lead author on this paper, which is still in preparation, but it shows the solubilization of carbohydrates from winter rye that were harvested at various degrees of maturity. And so here we have mid-April through mid-May. And don't worry a lot about the different nitrogen treatments right now. I'm going to come back to some of that. But this is with Clostridia thermocellum that they're using as a consolidated bioprocessing organism, and here's a conventional yeast in a solid state co-fermentation. So maybe it's not a conventional yeast, but it's a co-fermenter. And what you see here is the soluble sugar and then the insoluble sugar that has been solubilized. And you see in their organism there's a higher amount of that insoluble sugar. But you also, what I really want to point out from the purposes of thinking about these immature grasses is the slope of the total hydrolysis that occurs during this period. And I should mention that this particular cycle over here is without conventional pretreatment. So with the immature grass, we're actually getting roughly 80%, 70 to 80% solubilization of the sugars in the plant of theoretical values without pretreatment. So that's pretty interesting. For those of you who know refineries, the pretreatment process is roughly 30% of the capital cost of the refinery and roughly 25 to 30% of the operating cost. So if you can eliminate that, it's a big target. Now, the other thing that's kind of interesting is as we scale up these cellulosic feedstocks, we're going to have to think about how to harvest and store them. And this is some DOE analysis of what the moisture content will be at their view of optimum harvest time, which is actually after the plant senesce, in many parts of the country. And this would include a mix of corn stover and switchgrass, and I'm not sure if the scanthus was included in their analysis also. But particularly the corn stover, it dries a lot more slowly than the grain, so it actually reaches low moisture content much later in the fall. And so depending on the grain harvest strategy, and there's a lot of interest in what's called single pass harvesting, where you harvest the stover at the same time as the grain, reduces a lot of the operations on the field and soil compaction, et cetera. Then you're going to end up having stover that's well above 20% moisture, probably 30 to 40% moisture, and that is really hard to store dry. And if you have to use electric energy or gas energy to dry it, that's going to change your footprint quite a bit. So there's a lot of the U.S., and I live over here, but obviously there's a lot the other side of the Missouri River, and especially the east of the Mississippi, that's going to be in that 25 to 40% moisture range, which is going to be pretty hard to dry and bale in a conventional dry storage system. So I think there's a logistic challenge that's going to be out there that may drive us to thinking about some of these wet materials and thinking about wet storage as an alternative. That's an area that I've been doing a lot of work on. I'd be really happy to talk about it more with some of you. I don't have time to get into those details today. But I did want to take just a minute and talk about winter rye some more, because I do think it's a pretty interesting opportunity. Andy Heggenstaller, by the way, is now working for DuPont, and he's been collecting the corn stover that's going into their refinery that they're opening in Nevada, Iowa this year. So he stayed in the industry. So this is some analysis he did of winter grain. In this case, he was working with triticale, but so it's a cross of wheat and rye. So the idea here conceptually is that we're growing the plant during the summer. At some point, the crop stops capturing solar energy and starts to die back. And there's a period in the winter and spring when we're really not taking very much advantage of the solar energy that's coming down and landing on the field. We see that particularly with corn. So when's the summer solstice? Quick quiz. June 21st. All right. So many of you seen a cornfield. When's it close in? The canopy close? July. Yeah, the plant's knee-high by the 4th of July. That was an old saying. It's really now waist-high by the 4th of July. But anyway, so actually half of the summer growing season in terms of solar energy is already passed before the canopy closes. That's one of the reasons we're so excited about perennials. But these winter annuals can actually help the overall system capture some of that light in both the spring and also the fall. And here's what that looks like. So here we're capturing a little bit in the fall, and then a lot in the spring, and then do a harvest right before we get our summer annual in the ground, and maybe even we can even interplant that summer annual if we work out the techniques appropriately. This is a little bit hard to see, but the purple is the treatment with just a typical summer crop, and this is soybean. And then here's winter rye, the black, which you see the purple went like this, and all this extra biomass accumulation is from having that winter crop capturing sunlight in the fall. And these are some yields, so metric tons per hectare, so you can roughly divide by 2 to get tons per acre, which would be in the sort of 2 to 4 range. But you can see that this stage right before flowering there's a little bit of a burst there in terms of yield, and then it pretty much flattens out. And you can harvest at the end of April or early May and still get your summer annual crop, your corn or your soybeans, in the ground in most of the U.S. In fact, I'll show you some of that data in just a moment. Here's some work we've done on looking at the energy inputs and energy outputs from traditional first-generation fuels. So this is corn-soybean rotation going to corn ethanol and soy biodiesel. The circles are actually scaled to the amount of inputs and outputs. You see we are including the processing, so here's corn ethanol processing and biodiesel processing, and this is the energy input on the farm. And then the energy content of all the outputs, the energy content of the fuels you're probably used to thinking of, but this is on a calorie basis, the energy value of the distillers dry grains and solubles, the soybean meal, and the glycerin, which is a byproduct from biodiesel. If we add rye to that, no, actually I'm going to go back and just ask you to remember for just a moment the energy input, the energy output, but most importantly the net energy value. So this system, the conventional system, is getting about 23,000 megajoules per hectare and a ratio of outputs to input of 1.6. So we add rye to that system, and I will say we also are adding cellulosic technologies, so we're going to use some of that corn stover also. And the combination of those two things bumps us up to 60,000, so more than doubling, almost a tripling of the energy on a megajoules per hectare basis, and the ratio jumps up to almost 3.5. So pretty big improvements in this corn-soybean system that actually covers a really big part of our nation, and also causes all kinds of environmental issues because of winter fallow right now, where there's a lot of erosion, loss of nutrients into the Mississippi. I'll come back to that in a moment. So we did some analysis to scope out nationally what the potential was like. We did a sort of constraint-based analysis, so we looked at the corn belt, and we narrowed that down by looking at just the counties where more than 2% of the total county area is producing corn or soybeans. We then narrowed it further by taking away the areas where there's a lot of irrigated corn or even a modest amount of irrigated corn, so up to if there's more than 5% irrigation, we took that away. Those are the sandier soils and the places where a winter crop might actually be soaking up moisture that the summer crop might actually need. All right, so don't want to get into those areas. We looked at areas which already has winter crops, so rice and cotton were two that we took out of our list. And I should mention that we also pulled off the other winter wheat and winter barley, which we understand are, obviously also part of the situation. And then this is what we had left, and we did some modeling of what the winter rye would be based on typical planting dates of corn and soybeans and typical harvest dates. We looked at the window between those two, and we provided a 7 or 14-day buffer on either end, so you could actually get out in the field and plant the winter rye and then harvest it at the end. So here's that analysis with the 7-day scenario. And you can see a pretty big part of the country in sort of 3 to 4 megagrams per hectare, which is modest. I mean, this is not 20 tons per acre. This is maybe 2 or 3. But still a significant amount that you can add to your existing production, and those numbers get a little bit higher depending on the rotation you're in, and quite a bit higher for the corn rye going into soybean rotation, because the soybeans can be planted later and are typically planted later, so you get a lot more growth of the annual crop. And when we looked at the 7-day scenario, and averaged that whole rotation of depending on which cycles there were, and then summed it up, we got somewhere between 120 and 150 million metric tons, dry metric tons, of biomass produced on existing food land, but taking advantage of the winter fallow and creating an energy crop that could actually be harvested next year or the year after, and scaled up in a very rapid way because the farmers are already growing this stuff, right? So we're pretty interested in that. We're focusing a lot of effort. Now, most of you don't think of Pennsylvania as a Corn Belt state, probably. We're not always in the Midwest, but some folks over here next to Ohio actually are Midwesterners. But we are over in the eastern part of our state, in the Chesapeake Bay watershed, and that, as many of you know, is a very important estuary, most productive estuary in North America, even more productive than the Bay, although the Bay used to give it a run for money before they filled in so much of it. But in any case, there's a lot of interest in improving water quality, and so we're working with the Chesapeake Bay Commission to think through how these winter annuals might actually provide some water quality benefits that they might help to subsidize to reduce the cost of producing the cellulosic biomass. There's been a lot of questions about winter rye carbon and nitrogen dynamics, so this is some preliminary data of a paper we're just working on right now. Amanda Ramcharan's one of my PhD students who's done the analysis with Armin Kamanian's crop model. And I'll just run this through pretty quickly. So we're looking at corn-bean rotation with winter rye in between the corn and soybeans on both after each summer crop. And then we're looking at fertilizer N applied to corn only versus fertilizer applied to corn and additional fertilizer applied to the rye to achieve 75% of its potential yield. We don't want to dump a lot of extra nitrogen on the rye because in a year when it's not achieving its total yield, we don't want a lot of extra to run into the water supplies and create a worse water quality program, so we're kind of starving it a little bit for nitrogen in that analysis. And we're starving it a lot for nitrogen in this analysis here, although I will say we got modeled 2 to 4.5 dry tons in these different scenarios. So you'll see some different data here. Rye, where we're harvesting the rye in each case, but not the corn stover, versus rye stover, where we take the corn stover off and then skip a year, don't take off the summer rye, but then take off the rye the first year, but then do the second year. Okay, and so then that's repeated again with the higher fertilizer rates. So here's some data. First on nitrogen use efficiency, and I want to start with a baseline. So here's a conventional winter fallow system with a nitrogen use efficiency, and I should mention that we looked at both low and high organic matter soils and at 3 different locations in Pennsylvania and Maryland. All right, so that's why you see these distributions in terms of nitrogen use efficiency. And but in any case, roughly 0.6 is where the systems are, conventional systems are today. And nitrogen use efficiency is the nitrogen you get out with your crop versus what stayed in the system. So actually, with the winter rye, with the conventional cover crop and spring tillage, we're not harvesting as much. So this isn't all lost from the system, and some of this will carry over, but we're not getting as much crop nitrogen out of the system as we would with a conventional system. So that may be a little bit misleading. We could talk about it more if you have questions. But then I want to get to the rye stover and rye options. So here's the rye stover option. So by harvesting the stover after the corn and then the rye after the soybeans, we end up with nitrogen use efficiencies closer to 0.75. So that's a pretty significant jump. And then with the rye in between, so roughly 0.65 to 0.65 is kind of the mean there. And if we add the extra fertilizer to get up to 75% of the potential rye yield, we're back into that 0.65 range with the rye and with the rye stover down a little bit below 0.6. All right, so there's some differences there. But at least these 3 scenarios look pretty interesting as a benefit above and beyond, or a benefit in terms of nitrogen use efficiency relative to our conventional summer annual cropping system. I'm not sure what that was, but all right. So my conclusion here is not a big surprise. Adding fertilizer increases and losses. Okay, but these intercrops and the idea of these winter crops can actually complement things, including the corn stover harvest. And then the other point was that the rye is still similar to fallow, even with the extra nitrogen. Soil carbon. Now that's interesting. When you think about taking all this biomass off of the ground, there's concern that we might be taking more than we actually have. So what's going to be the long-term soil carbon impact? And these were run for actually many simulated cycles, many years until we reach steady state. So these are long-term changes based on these soil types and these crops. And what you see is, and I'm not going to take time to go through all of these, but in general, our conventional system is actually not doing the soils a big favor. So if we run corn, soybeans without cover crops, we're going to see a decrease in soil carbon in most cases. There's a lot of error bars here. We did lots of stochastic work on this. And the cover crops tend to move us into the positive directions. But interestingly, so without the fertilizer, the rye and the rye stover both look a lot like the fallow system, but maybe bigger decreases, so we really need to get a handle on that. But more likely to have a positive situation when we have a fertilizer or a smaller negative situation. I should mention that one of the interesting things I want to spend some time thinking about this semester is what's the right time frame and how do you think about these long-term equilibria when we start to charge our fuels with the carbon changes on the land. And that's part of the indirect land use question, but in this case, it's a direct land use question. So, and again, not a big surprise here, but adding fertilizer enhances the storage. Actually, that is a big surprise because when I get to one of my later questions, and I'm going to go really quickly to get to it, we'll find that that's a management opportunity that I think we need to pay more attention to. Yes?
Question. Just to be clear, those are model results.
Those are model results. We do have some field data that we calibrated with, but not all of those different scenarios.
And have you accounted for microbial response to enhanced fertilizer use as well?
Yes. So the carbon-nitrogen ratio in the soil affects our carbon degradation function. All right. So I took a little bit longer than I wanted to on that, but sugar and syngrass, I mentioned that there are some other platforms to think about. I know there's some work going on here, or will be soon, on biogas. Methane to methanol and methane to other fuels is pretty interesting, and that's a topic which I'd be happy to talk to anybody about. We're working with a couple of companies, Praxair and Primus Green Energy, that are both looking at thermochemical conversion of methane plus syngas into fuels, and the blends actually have some really interesting properties in terms of maximizing the carbon conversion, minimizing CO2 losses during the refining process. I want to spend just a couple minutes on carboxylic acids, and this is something we've been working with through a process that's a lot like anaerobic digestion that we use to produce methane, but we truncate it. We don't encourage the methanogens to convert the carboxylic acids into methane. Instead, we harvest those acids. And it's actually not that hard to discourage the methanogens. As some of you work with them, they're pretty feisty or pretty sensitive organisms, and so easily upset. So here's some data, and this is by no means an optimized system, but these are a suite of carboxylic acids, including a lot of hexanoic. That's a 6-carbon chain. And this is total acid yield on a mass basis relative to the grams of biomass fed. So you can see we're getting after 21 days, and this is, by the way, a very low-cost fermentation process. We're using a mixed culture, non-sterile environments, the sort of thing you could basically build a big pile someplace and operate. And oops. So we're getting, again, with an unoptimized system, roughly 55 to 60% conversion into acids, and these are just a couple replicates here. And the thing I also want to draw your attention to is that from those acids, if we're going to another fuel, we can get actually some pretty good conversions. Actually, these are the sugar to acid conversions. So we're actually not far from theoretical, given how much of the 6-carbon the hexanoic acid we have. So anyway, that's pretty interesting, and we're probably in the same range right now as what ethanol fermentations are looking like. All right, so again, I shared some of this before you today, but my next question was about food and fuel, and is there enough room? And really the bottom line here is there's an awful lot of excess consumption of food in the United States, I'll put it that way, all right? And so we looked at, yes?
Was the data you showed us on biomass, sugars, what was?
Oh, that was willow biomass. Okay. Yep. So it was cellulosic willow. It was pre-treated with a hot water pre-treatment process. Yep. Sorry, I didn't cover that. So I'm just very quickly going to mention we looked at two diets. One was the U.S. Dietary Guidelines, which came out a couple years ago, the food plate. Many of you know that. That's what the USDA thinks is a good, healthy diet for Americans. And then the other is an analysis looking at a reduction in the protein fraction supplied by beef to 17% and making up the balance by chicken. And I'll just mention that that's a trend that's already been occurring. We've already seen actually a 19% drop, more than that by now, since 1975, in terms of the fraction of the American protein diet that is beef. So there's been this big shift from beef to chicken. And it turns out chicken are a lot more land-efficient way to grow protein. So that turns out needing a lot less land. Here's the average U.S. diet, circa 2010. And this is on the basis of both calories over here and the land required for those calories over here. So those of you who weren't at my presentation a couple years ago, this is like probably a big shocker to you. Here's the beef fraction of our calories, and here's the beef fraction of the land that we use for producing food. Now, I'm coming out of 5 generations of collar ranching. So I was back in my ancestral town this summer, hanging out at the corral. And so I'm not against beef and ranch land. But I do recognize it's a pretty inefficient way to use cropland to produce meat. And I will say also that 2/3 of the land in this is rangeland, all right? So, but roughly 1/3 of it is cropland. We fatten our cows on corn and soybeans, and that's not a very efficient thing to do. We can get a lot more chicken from those chicken protein from those corn and soybeans. And in fact, when we look at those diets, and again, I'm not going to take a lot of time, but here's those shifts I mentioned. The basic, this is the status quo diet versus that protein shift. You can see here's the reduction in beef by half, and the increase in poultry to make up for it. And then this is more complicated, but I've highlighted in red and green some of the big changes in the dietary guidelines relative to conventional. Big increases in dairy, pretty substantial decrease in beef, obviously both same species, so, but anyway, lots more fruits and vegetables as well. And I'm going to just kind of skip across this, but to point out that on the land basis, that when we redo these diets, here's the status quo, here's the USDA food plate dietary guidelines, and here's that protein shift from beef to poultry. What we see is the amount of hectares required, millions of hectares required to grow food in the U.S., and by the way, we held all the non-food and exports constant in this analysis, goes down from 415 million hectares to 369 for the dietary guidelines, to 355 for the protein shift. So those are roughly 15% decreases in acreage from trends, in this case, that are already occurring or that probably should occur if we had a more healthy society. We then modeled switchgrass and miscanthus and how much could be grown on the cropland that would be liberated by these changing diets. And again, the beef poultry change is already occurring. I'm going to just take a slight second to step out and say, you know why corn ethanol is out there right now? It's because this change started in 1975, and by the mid-'80s, the corn industry was running out of cows to feed corn to. And they needed another market. and they knew that the American diet for corn was satiable, but the American diet for energy looked insatiable. So you can look at what happened, and the corn growers got real excited, and away we went. So this isn't the first time this might have happened. And we then modeled and looked at how much could be produced by these protein shift versus dietary guidelines using current yields of switchgrass and miscanthus versus the kinds of yields that some of you might be projecting in a future scenario, and looking at current process technologies in the white bars and more efficient process technologies, again, that some of you are working on into the future, and looked at how much of the U.S. gasoline and diesel combined in total transportation could be satisfied by the biomass produced on existing cropland that is not needed to feed Americans a healthy diet. All right? So that's pretty interesting, a lot more than 30%. All right, so I'm almost done. Essentially last slide, because this is what I'm going to be working on here. And I really want to sort of tease out this question about these transitions and what happens to land, and if we had 100 million hectares of cropland that we didn't need anymore, should we just let it go back into prairie and forest, or should we manage it for biofuels? So I mentioned earlier that management can actually enhance yield. Natural ecosystems do pretty well, but fertilizer is a pretty powerful tool. And when we look at the biofuel carbon benefits relative to the biomass carbon produced, there's a ratio of roughly about 0.6 when you account for the carbon dioxide losses in the various supply chain and conversion processes. So essentially, to make biofuel production a better alternative to natural landscapes, those biofuel systems have to be at least that much more productive. All right? So it's a hurdle, but it may not be an impossible hurdle. I think it's actually a relatively easy hurdle. So I'll be working on that. And I did want to share, and Bill Stewart has some data here for California that some of you may have seen, but this is some analysis the IPCC did actually back in 2001 showing the way to think about forest biomass from a long-term management perspective. And one of the things that you would see over time is that forests would grow but then stabilize over time. And in this case, if you manage it by harvesting it and then converting that forest into fuels, into products, and some of those products eventually end up in the landfills, and growing a second forest crop, you end up creating a system where every time you grow that, you end up displacing fossil fuels, creating sequestered furniture and buildings, and also growing more plants. And that combination of benefits is something which a lot of the ecosystem analyses aren't incorporating. So I think we need to kind of pull that whole package together in a coherent way. All right, so there's a summary of my 5 myths. I gave you a little bit of teaser. I'm not sure if we're allowed to go a few more minutes. I know there's lunch out there.
Yeah, there's lunch out there. Let's do 1 or 2 questions here, and then we can continue questions over lunch.
I'd be very happy to take more questions over time, too.
So let's thank Tom first.
Okay, so does everybody believe my analysis on all these myths? I want some skeptics to challenge me. Yes?
So I'm going into this purely from a molecular biology and science point of view.
Great.
So I'm quite convinced in the US that if dietary changes continue, bioethanol looks like you can grow more fuel, but what about on a global scale? What about, are we going to see increasing biofuel in other parts of the world, especially Africa?
Great. So let's unpack Africa a little bit, all right? So Africa, as some of you know, has got actually a tremendous natural resource base. It also has a population that's in many places severely disadvantaged, and food security is a big issue, all right? So A lot of the challenges to food security are not about the resources, but about the management of those resources. And there's big issues with politics and with market forces that are not supporting the kinds of development that we'd like to see. Just to give you sort of ballparks, and some of you know John Foley, who's a geographer and is now actually executive director of the California Academy of Sciences across the Bay. So you might want to invite him over here sometime to talk. But he's done this analysis looking at the yield gap in different regions of the world between what we know we can grow with current technology and what is actually grown. And that gap here in the United States is somewhere like 10 or 15 or 20%, but in Africa it's closer to 75%. So we know that we could quadruple the production on existing agricultural land in Africa, and that would be more than sufficient to supply. And actually, if we even tripled it and got it close to where we are here, that would be more than sufficient. My own view is that biofuels actually create some interesting opportunities to improve the infrastructure for agriculture more generally, to create supply chains for fertilizer and other inputs into underdeveloped regions, and also market opportunities to get things out. So I think there's an interesting compatibility there. I'll also note that there's a Gates Foundation project right now that's been working in Kenya and Uganda and I think Ghana, and they've managed to more than double yields on smallholder properties in just 5 years. So I think there's some really interesting opportunities there. I don't think it's an easy problem, but it's the kind of problem we need to take on as a global society.
I think we'll adjourn and move on to lunch, and anybody who has further questions for Tom can ask him now.
Okay, great. Thanks.